Hello, I am Siddhant Attavar and I am from Karnataka, India. Today, I would like to talk to you about my project, SMART, Stroke Monitoring and Rehabilitation using Technology. My interest in the subject was triggered when a close relative suffered a cerebral stroke and began undergoing a long and challenging rehabilitation process. As I researched more on global stroke statistics, I realized that cerebral stroke is indeed a major global healthcare challenge. In fact, stroke is the second largest cause of death in the world, with 15 million cases every year and 5 million fatalities. Those who suffer a stroke face numerous other challenges like permanent disabilities and lower employment opportunities. The problem is even more acute in low-income countries like India due to lack of awareness, poor accessibility to stroke care centers, high costs, and a shortage of medical personnel. A survey conducted in 2016 also points out the key challenges faced by patients and the need for low-cost, accessible stroke care services. Stroke experts too have often emphasized it is crucial for low and middle-income countries to develop technology-driven rehabilitation strategies to meet the growing needs of stroke survivors. My project SMART is an innovative, low-cost solution that has been developed to address these very challenges by facilitating rehabilitation at home for stroke patients. The SMART package consists of two parts: a DIY EEG headset that records brainwave activity and a smartphone app that analyzes it. EEG is a non-invasive method of monitoring brainwave activity. However, medical EEG devices are often expensive and not portable, and therefore are not suitable for home usage. So, I have developed a DIY EEG headset using 3D printing and low-cost electronic circuits. Using the Tinkercad software and a Flash 4 3D printer, I was able to develop an ergonomic, rugged headset that can fit varying head sizes. Following extensive research, I identified certain low-cost and easily sourced electronic components to build the DIY EEG device. 3 silver chloride electrodes placed on the foreheads and behind the ears on the mastoids. A microelectronica 3359 IC for the amplification and filtration of weak biosignals. This IC consists of an instrumentation amplifier which has a gain factor of 12x and the filtration module which amplifies the signal further to make the final factor 7800x and uses low pass and high pass filters to eliminate noise interference. This noise interference could be caused by numerous sources like muscle movements or external electrical appliances. Finally, we have the Bluetooth-enabled Arduino board for collecting and transmitting the signal to the smart app. The EEG data collected by the smart headset is relayed via Bluetooth to the smart app. I have developed an algorithm in the smart app which analyzes the raw EEG data. First, we perform a fast Fourier transform to get a frequency distribution of the data. This frequency distribution is then divided into 4 brainwave bands, namely beta, which is from 12 Hz to 25 Hz, alpha, which is from 8 Hz to 12 Hz, theta, which is from 4 Hz to 8 Hz, and finally delta, which is from 1 Hz to 4 Hz. For each band, we calculate the respective relative band power. This can then be used to analyze the patient's brain state. The Smart app has been designed using Android Studio. It is easy for patients to use at home and for doctors to remotely monitor the patient's progress. With just a few clicks, the patient can access diagnostic tests, rehabilitation modules, and take charge of monitoring their own recovery process. The delta alpha ratio, or DAR, is a common metric used to measure a patient's cognitive function. A recent study showed that stroke patients have a significantly higher delta alpha ratio than that of non-stroke patients, as shown in the graph below. They have recommended that a DAR level of 3.7 can be an effective threshold for identifying stroke patients. I have developed an EEG-based diagnostic test in the Smart app, which measures the patient's delta alpha ratio and uses this to identify stroke patients. The test consists of 3 steps. First, we record the brainwave activity, then we calculate the delta alpha ratio from the data received, and finally we compare it against the standard threshold. Although this test is not as accurate as an MRI or a CT scan, it is extremely useful in rural areas where brain imaging is not readily available. A 2019 study showed that higher levels of alpha activity are associated with positive rehabilitation outcomes. As we can see in this graph, by increasing the alpha levels of patients using neurofeedback training, a consistent improvement in the cognitive performance of patients was recorded. I have designed a simple, interactive game that trains patients to maintain higher levels of alpha activity using neurofeedback training. This game uses SSVP, or steady state visually evoked potentials, to induce the alpha brainwave state. The SSVP system consists of a light that flashes at the rate of 10 Hz. When the patient sees the strobing light, the brain mimics this frequency, resulting in an increase in the alpha power. In order to test the reliability of the SMART EEG headset, I performed a series of tests. First, I compared the raw EEG data from the SMART EEG headset with that from an external dataset, confirming that both readings were in the same range. For the second experiment, I used an SSVP to test whether the SMART EEG headset is able to detect changes in the brain state of a patient. I first recorded the beta level of a subject with no external stimuli. I then introduced an SSVP to increase the beta activity of the subject. As we can see in the graph at the bottom, this change was immediately recorded by the SMART EEG headset. In the future, I plan on adding more features to SMART to make it a more comprehensive solution for stroke care. Firstly, we can improve the accuracy of the SMART EEG headset by improving the type and number of electrodes used. Motor training is a key part of stroke rehabilitation. We can provide quality motor training by leveraging technologies such as augmented reality. Cognitive training too plays a vital role in the stroke rehabilitation process. I plan on developing cognitive tests that can be used to assess patients' cognitive skills remotely and provide feedback. Lastly, speech conditions often arise from stroke. Using machine learning, we can provide speech rehabilitation modules to help stroke patients with speech impairments. In conclusion, I believe that SMART can help improve the quality of life for millions of stroke patients across the world due to 4 reasons. It is a low-cost solution, less than $100. It provides diagnostic tests to identify stroke early. It allows doctors to remotely monitor the progress of a large number of patients at once. And last but not the least, SMART makes the patient an active participant and gives him control over his rehabilitation process. Experts say that this psychological factor itself can significantly improve patient recovery outcomes. Thank you for giving me this opportunity to showcase my project. I sincerely hope that SMART can become part of the solution to improve stroke care all over the world.